What's happening, everybody? How we doing? Got my hair's all messed up from basketball practice. Marcos Couch, what's happening? I guess you can't respond to me, can you? I'm excited. This isn't Zoom. I'm thinking it's Zoom. We'll give it another minute or two while we let this thing kind of get filled up a little bit. I'm missing the Iowa basketball game. Iowa is beating up on Wisconsin pretty good right now, so y'all better feel pretty lucky. That's all I'm saying. Make sure you've got some notes, some space. We're going to start where we normally start, and that's where we look and see where we've been. We look and see where we have been. So we're going to go look back at first semester energy and momentum unit. We're going to start there, okay? So it's 8 o'clock now. Let's get started. This one will be a little quicker because I just don't think this unit was as long. I don't think there was as much information there or new information there. I think it was mostly just kind of like old stuff rebranded, So that's where we're going to start. So let's get to it. Get the whiteboard out. I got my marker, my eraser right here. Let's get to it. Where have we been? Here's where we have been. Make sure y'all can see. Hopefully you can see. Hopefully it's not too dark in here. Hopefully the blue shows up. But where have we been? Here. First semester, we talked about energy and momentum and the two big concepts that have carried over from first semester into this unit, the rotational energy and rotation and angular momentum unit, are KE, kinetic energy, and momentum as well. So back in the day, back in first semester, we're talking about objects that move on lines, translation of motion. So that might be something moving on an arcing path, but XYZ motion, right? Linear motion. We say that the kinetic energy is equal to 1/2 mv squared. These were our linear variables that we use when objects are moving in the X, Y, and Z direction. For momentum, we said that P, or for my super nerds, it's actually a rho, a Greek letter. Rho equals mass times velocity. These were our variables. We also had changes in energy and momentum because we know that these things are not always conserved based on the shape and size of our system. So we have work. Work is a change in energy, and work was defined as a force that acts on a distance or over a distance times cosine theta. So this is the parallelness of the vectors, right? Force and distance need to be parallel to each other for work to be done. If you think about torque, torque is actually force times R times sine theta because we want those things to be perpendicular to each other. So that idea of like parallelness versus perpendicularness is not a concept that's super important, but it's also, when you think about it, kind of makes you go, oh, force sine versus cosine, right? Unit circle stuff, scary stuff, but still, I'm seeing some connections between like cosine and sine and what these physical values mean. The big idea, force causes over a distance, causes a change in kinetic energy. Impulse was the term we use for change in momentum. Impulse is not momentum. It's a change in momentum. That's not an X. That should be a V. That's my mistake. And again, impulse is the result of a net force over a period of time. Instead of distance, now it's how long did that force act on the system for? Well, that's my change in momentum. The big takeaway from first semester was these things remain constant unless there was an outside net force acting on my system. Now, obviously, collisions were a weird one, right? When collisions happened, energy wasn't conserved. Well, mechanical energy wasn't conserved. Energy gets converted into heat, into sound, into deformation of objects. So energy is conserved unless an outside force acts on it. Again, mechanical energy, or a collision happens. Momentum is always conserved in a system unless an outside force acts on it. Now, we didn't have forces necessarily this unit, right? Forces were this idea, like we kind of translated forces over into torques. We said there are forces, absolutely, but when those forces act on a lever arm with a fixed axis of rotation, we call those things torques. So we're changing over our idea from forces to torques. And so what you'll see is that this phrase, second semester, can just read, changes occur in rotational kinetic energy or in angular momentum when an outside net torque acts on my system. It's the same concept. We're just changing the flavor. We're just changing the vocab words, okay? So let's talk about where we started. Again, I usually walk through some of the labs that went down in my class, so that's what we're going to do here. We'll talk about some of the labs we saw. So here's where we started. We started with energy, In the first lab that we started with, I'm actually probably going to turn this thing sideways. Whoop. The first lab we started with was sliding down or rolling downhill. So we had an object, either a ball or a hollow disc, a cylinder of some kind. We rolled it down a ramp. Let's go ahead and draw our FBD. Like always, FG, FN. Notice their locations are not both at the center of mass, but the axis of rotation is at the center of mass. There also was our friction force, or static friction pointing up the ramp. This was our setup. We compare this to like something first semester that has an object that doesn't roll. And we go ahead and draw our FG. We draw our FN, our force. This, though, if it's going to slide, is called kinetic friction. So this is a rolling object because it's round, and this is a sliding object. And as we think about this, I believe the demo we did, if you were in my seminar, most seminars did this. If you were in my class, the demo we did is we sent this rolling ball down a ramp and we predicted where it would land. So we sent it on the ramp, we launched it off, and we said, okay, let's track some energies, y'all. And so we said UG is going to be equal to the kinetic energy at the end of the ramp as it launches off. And then we use kinematics to predict where it would land. And folks, when we did this, when we said UG equals KE and solved, that object landed like there. And our minds were blown. What in the world just happened? My math is not, sometimes my math is that bad. My math is not that bad. What we came to understand was that there was a new form of energy we hadn't quite considered yet. We hadn't quite considered that rolling had its own type of energy. We hadn't quite considered that there was a translational or a linear kinetic energy, and there was a rotational kinetic energy. As the object rotates, it also stores some of the UG. There's also some internal forces taking place that store or transfer kinetic potential energy into kinetic rotational energy. And so we know that our equation for UG is mgh. We know that our equation for translational kinetic energy is 1/2 mv squared. We needed a new equation for K rot. And so what we tried out to see if it worked was like, let's just replace M and V with our angular variables. We have mass, but we're not really talking about mass when things are rotating. We're actually talking about rotational inertia. It's the shape and the mass distribution that we talk about in angular motion, not so much the mass of an object. And we don't talk about V necessarily when things rotate. We talk about omega or angular velocity. This was in fact our rotational, our kinetic rotational energy equation, 1/2 I omega squared. It looks real similar to 1/2 mv squared, but this is what we found. Now, let's compare that. Let's compare that to what it looks like when we're sliding down a ramp. If we were going to slide down the ramp, we would say UG is equal to kinetic energy. Now that's true if there's no friction on my ramp, but I already said there was friction, right? There's a force of friction, so I can go ahead and say, you know what, mu is not equal to 0. So let's rewrite this. UG minus the work done by friction is equal to the kinetic translational energy. There's a big difference here, right? Like there's a giant difference here. The first is like, wait, what? There's work done here. Like there's work done on the box by friction. But over here, there still is friction, but there's no work done on the box. Let's think about that. What is the distance that this edge, if we remember that work is force times distance, this is what work is. If we recall that, this edge of the box stays in contact. There is friction that occurs from here all the way down to the edge of the ramp. That friction occurs over that distance d. Let's think about this edge. Where does this point? Where does this edge of the circle? Over what distance is that force of static friction acting? Well, we know that every part of my circle is at some point going to come in contact with my surface. It's rolling. There's static friction. There's no slipping. We are rolling without slipping. So is there a force acting over a distance when something rolls? The answer is no, not really. So what causes something to roll? it has to do with where its axis of rotation is, where its center of mass is, and how it's offset from the point of contact on the floor. It's like when you try and balance a Pepsi can or a soda can on its edge, but you haven't sipped enough down yet and it tips over. And if you haven't tried that, you're already on YouTube, go check it out. Like, you can get something to balance when its center of mass is located beneath the point of contact with the surface. On objects like round objects on angles, the center of mass is located offset from its point of contact. That thing's going to tumble down the ramp without slipping. So, does static friction cause work? No. Why not? There's no distance that it acts over. So these are the differences that we came across in terms of things that rolled down ramps and things that slid down ramps. We lost energy due to friction here. And over here, we didn't lose any energy to friction, but it was stored rotationally. Okay? These were the primary differences that we saw here. One other strange thing is that if I wanted to write my F net expression for my ball rolling, it would be Fg parallel minus the force of friction static, because it's still opposing it, it's still up the ramp. That would help me find my acceleration. On the flip side over here, this F net equation looks like this: Fg parallel minus force of friction kinetic. Their F nets look incredibly similar. The only difference between them being static friction and kinetic friction. And we can still use these equations to find acceleration for the objects down the ramp, albeit linear acceleration, not rotational acceleration, unless we bridge them. But right now, these equations can be used to find the linear acceleration down those ramps. A follow-up to that discussion is an interesting conceptual question that we covered in seminar. And it looked like this. And if you have access to my notes because you're in my class, you can go see it. But it looked like this. I had two ramps. One like this with a ball at the top, and one identical ramp like this with a block at the top. Friction is not negligible. There's friction on both of these. And the question is, which of these, when launched off the ramp, will reach a higher apex? This is an interesting question. Let's look. If I track my energy, I tell the story of the ball. The ball starts above the surface of the earth. After a little while, it reaches the bottom of this well. At the bottom of this well, it's moving both translationally and it's moving rotationally. As it leaves the ramp, it is still moving translationally and rotationally. So I can track this from point A to point B right as it leaves the ramp. We'll call this A. We'll call this point B. Interesting. We'll call this mass M, and we'll call this mass M as well. Over here, this has no friction. So we'll say there's no energy lost to thermal over here. Well, let's track it. The box starts above the ground, the same height above the ground as the ball does. Eventually, it reaches the bottom of the well and it hits the ramp. So it's going to be moving translationally at this angle, the same angle as the ball. Which of these has more translational energy to carry it up here? Well, the one with translational energy only left over, right? Like, this is pretty clear to us when I write my energy expression out, that this one is spinning. So some of the energy that was stored potentially gravitationally is not going to be moving linearly. So we'll see this object be spinning and travel to a lower apex than this object over here. Here's where it gets super weird. Let's imagine now that this ramp doesn't actually end, but instead it comes back up to its initial spot. It goes back up to the initial height. Let's track our energy now, and we'll call this point C. If we call this A, this is point B, that's point C. There's A, this is point B. At point C, At point C, this object is rolling. It's rolling really quickly down here, moving translation really quickly. Eventually, as it starts rolling back up, it's raising itself above the surface of the earth. When it reaches point C, the same height it started at, all of the energy will return to UG. It will come to a stop, both linearly and rotationally. And the same will actually happen here. We'll slide down like a roller coaster and go back up to the top and come to a stop again. So this is weird. If the ramps continue, both objects go to the same height. If the ramps go from A to C, and those are the same height, both objects make it that high. But if the ramp ends at point B, well, then the mass actually makes it higher than the rolling object. And why? That's because of this new energy we've discussed, known as rotational kinetic energy. The object is spinning, so it's not moving completely and only translationally. Translationally means linearly. The last giant thing that we did using energy alone was we revisited our Windmill Lab. Our Windmill Lab looked something like this. Now, I'm no artist, but it was a giant windmill. We had some masses at the tips of these blades, and around the inside, we had a string and a mass hanging off of it. Now, we let that mass fall, a height of h. Let's try and come up with a conservation of energy expression for these two objects. So we know that the mass is going to fall. So let's start with the initial energy, right? At the starting point, there's UG of the mass. The windmill isn't moving, the mass isn't moving, it's just at a height above the ground. Got it. After we drop the mass or we remove our hand from the mass, things start to move. The mass starts to fall, which means the gravitational potential energy starts to decrease. And as it starts to decrease, the mass moves faster and faster. So we get this kinetic translational energy. It's moving on a line, linear motion, kinetic translational energy. But we can't forget that this whole windmill is actually starting to rotate clockwise as the mass falls. So we have to remember that things are being stored rotationally as well, okay? Let's go ahead and take this one step further, because typically these types of equations don't do well for us. Let's go ahead and start plugging some values in to see the importance of keeping track of some things. Okay, so I've gone ahead and I plugged in mgh for UG, I've plugged in 1/2 mv squared for KT, and I've plugged in 1/2 I omega squared for rotational. Let's keep going. Let's bridge this over to V over R. Let's change my I value into, I'm not sure what the windmill is, but let's for now just call it a hollow sphere. I'm sorry, a hollow disc. Let's just make it up. Let's just say that the I of the windmill, I of the mill is equal to, let's just say it's 1/2 mr squared. I know it's not. You don't need to tell me in the comments. I know it's not, but let's imagine for a second that it is. Let's keep plugging some things in. mgh 1/2 mv squared plus 1/2 times 1/2 mr squared times V over R squared. Now, hold the phone. This is a problem because a lot of times, especially in the stress of an exam or an AP test, we're going to look at this and go, all right, I see mass in every term. Here we go. Mass, mass, mass. Mass cancels out in this problem. Hold up. Remember where we started. This was the mass of the hanging mass. This is the energy of the hanging mass. And this is the rotational energy of the windmill. Probably shouldn't call this M. I should call that W. What that means is that we are tracking energy in different objects. This is a point in time when mass, in fact, does not cancel out. So be very careful on tomorrow's test. Make sure you are labeling your variables like too much. Make sure we know exactly what variable you're talking about. Make sure you know exactly which energy you are talking about when you go ahead and write these problems out, both for the grader and for your own sake. Don't get confused on your own problem because you forgot to label something properly, okay? All right, that was energy. I mean, conservation of energy, no work done because force of static friction doesn't really do any work. I mean, that's it, that's energy. We did windmill problems, we got two-body problems, those are the concepts. Here's another concept from 6A. From 6A, we started with this. We defined net torque. We said net torque equals I times alpha. And this means if something is going to rotate or if something is going to rotate, accelerate rotationally, it needs an outside net torque. It needs this. If something's going to change its angular speed, it needs an outside net torque. And then in my class, we watched the fantastic Callista Choi start doing her ice skating. And she had her arms out, and she pulled her arms in, and she put her leg up, and all this crazy stuff. The whole time she was spinning faster and spinning slower. And I'm no artist, no one judge me, but all she was doing was on one ice skate on the ground. She had one leg out to the side, and she had her arms out like this. And then out of nowhere, she would like put both feet down on the ice and put her, like, actually she had one leg like, woo, and then both hands were like up over like this. And she would spin way faster. This was weird, right? For some reason, she would spin slowly when her arms and legs were out. But as soon as she like did that, I think she called it a toe catch or a heel catch. As soon as she did that move, whoom, she went way faster. So what's happening? There was no outside net torque. What in the heck produced an acceleration? This is super weird. And we came to realize, you know what? This thing breaks down. This thing isn't true so this thing doesn't work if I changes. If the shape of an object changes, it breaks down. It breaks down. Let's examine it closer. Why does it break down? Let's make some substitutions. T net equals I times change in omega over T. I'll do this. T net times time equals I times change in omega. Here's why it breaks down. This expression is only accounting for changes in angular speed, not for changes in I. We said, okay, fine. When things are moving rotationally, T net times time is equal to a change in shape or speed. This became our angular impulse expression. Where do changes in angular momentum come from? Outside net torques. Outside net torques cause changes in momentum. Okay, either a change in the shape or speed will, a change in net torque will produce a change in speed or shape. Okay, but without an outside net torque, angular momentum is conserved. And so oftentimes we're able to write this expression. If there is no outside net torque, initial angular momentum, which is L, is equal to final angular momentum. Meaning I initial times omega initial equals I final times omega final. This brings us to our first momentum, or angular momentum lab. Ours was the disc-on-disc collision. The disc-on-disc collision looked like this. I had a dark disc that was pretty heavy, and I had a spinning wooden disc below it. It was already spinning with what I'm going to call initial angular speed. After a while, we dropped the dark disc onto the wooden disc. And then they were both spinning with what I'm going to call final angular speed. And we were asked to calculate and prove that momentum was conserved in this kind of circular collision. So we did. We started here. We said, okay, L initial equals L final. Well, initially, the only moment, there are two objects, right? So there's the wooden disc and there's the L of the dark disc. And after the collision, there's still the wooden disc and there's still the dark disc. Initially, the dark disc had no momentum. So we cross that one out. We keep going. We say, okay, I of the wooden disc times omega initial of the wooden disc is equal to I of the wooden disc times omega final plus I times the dark disc times omega final. Both of the final speeds, because they're stuck together, are the same. So we made another adjustment. One more mathematical change. I of the wood times omega initial equals omega final times I of the wooden one plus I of the disc. And this points out a super important concept that if I'm trying to find the rotational inertia of an object, of a strange object, all it is the sum of all itty bitty objects that make it up. So this weird mass on mass or disk on disk shape, in order to find its rotational inertia, I can simply add both of these inertias up. All right, just a quick concept. From there, we just plugged it in. We said a disk is 1/2 m of the disk of the wood times r of the wood squared times the initial omega is equal to the final omega, 1/2 mass of the wooden disk times r of the wooden disk squared plus 1/2 mass of the dark disk times the r of the dark disk squared. Like this was it. This was the crux of the lab. Was this proven? And all I asked you to do was like take some data, plug it in, and prove that this is the case. Prove that this is conserved when compared to energy. If I took the energy, K rot of the wood should be equal to K rot of the wood plus K rot of the dark disk. If energy was conserved in this collision, and we know energy is not conserved, mechanical energy is not conserved in collisions because of like boom, boom, heat and sound, we were able to prove this is not supported because of heat and sound, and this, in fact, is supported because there's no outside net torque. In collisions, we know that momentum is conserved, but not rotational energy, not mechanical energy. Again, it's a collision. In my class, the follow-up to this whole thing was, okay, if it is conserved, then sketch me the 3 graphs. Sketch me the angular momentum graph of the wood disk, sketch me the angular momentum graph of the dark disk, and sketch me the angular momentum graph of the entire system. So let's go ahead and do that. I got 3 graphs. This is over time. Let's go L of the wood, L of the dark disk, and let's go L total. And again, we've seen these graphs before. We just haven't like seen them a whole lot in terms of angular momentum. Well, the wood disk initially was storing, and I'll draw a line, I got a dotted line to be like, this is where the collision happens. So initially the wood disk has all momentum because initially the dark disk has none. It's not rotating. There's no omega. After the collision happens, I see the dark disk speed up. The dark disk now has some angular momentum, and the wood disk actually spins slower. So it's going to have a little bit less angular momentum. How much less? The exact same less as the dark disk gained, right? It goes from the wood disk to the dark disk. What about the whole system? Ask yourself, was there an outside net torque when the dark disk slammed into the wood disk? No. I mean, there were internal friction forces, the friction forces that act between the dark disk and the wood disk for sure, but like those were inside my system. They didn't cause a change in momentum. I mean, they caused the change in momentum of the wood disk. It caused the change in momentum of my dark disk, but it didn't cause an overall change in momentum of my entire system. That means that the total momentum is equal the entire time. How equal is it? It should be the exact same number. We can call it LT that the wood was initially. They should have the exact same initial momentum values because all the momentum initially was stored in the wooden disk. This was our big takeaway. The last lab we did in class, and most of us did this one in class now, whether or not you were in my class or not, was the shoot and spin lab. Like I said to my class, we're not very creative physics teachers. What was the lab all about? Oh, we shot something at something else and it spun. Well, what did we do? We took the windmill, we put it sideways, and we put some magnets on it, okay? And then we had one of our little projectile launchers right here, and we launched a marble. Again, bird's eye view looking straight down. We launched a marble with an initial velocity, we'll call it V initial, at this magnet. All to support the idea, all to support this big idea that move linearly have angular momentum about an axis of rotation. Meaning, here's my axis of rotation. We wanted to support the idea that this object right here, in fact, had angular momentum around this at the point of collision. So when it hits right here, we wanted to prove that because it's moving on a line doesn't mean it doesn't have angular momentum, because guess what? When it hits this magnet, it produces angular momentum. So let's put this mass and our windmill in the same system. Here's our proof. We want to prove that the initial angular momentum is equal to the final angular momentum of the ball, of the ball and windmill system. That was kind of our proof. Okay, initially, where's the momentum stored initially? Initially, the windmill's not moving, so it can't be stored there. It's only stored in this ball right here. So I'll say, okay, if I'm going to prove this, I of the ball had better be equal, or times the initial velocity of the ball had better be equal to the I of the windmill times the final angular speed plus the I of the ball times the final angular speed, plus we can't forget about those stinking magnets. They're little, but we still need to think about them. All right? Weird. Okay, so this is getting strange. I need to think about this. What is the shape of the ball? Okay, I need to know the I value of the ball. And the reason this is so weird is because it's not a sphere, right? Like a sphere is something that has a shape like this and an axis of rotation inside it, where the sphere is rotating around itself like a ball rolling down a ramp. Okay, it's not a disc. I mean, it's a sphere. It's a solid sphere. So I get confused, like, what shape is this? We gave these shapes a very unique name. We called them points, or point masses. Point masses, for some reason, tend to confuse physics students. Here's how I define them. Point masses are just objects that rotate around an axis of rotation that is located outside of their physical space. For example, if you sit on your chair and it spins and you spin around that chair, your axis of rotation goes like right to the top of your head, right? If you take a golf club and you swing a golf club or swing a club around your waist, the axis of rotation is like your sternum, right? Those axes of rotation, those axes are inside you. This object here is going to rotate around an axis of rotation that is completely outside of them. This makes it a point mass. Our question is, this mass right here, how much, what percentage of that mass is distributed at a distance of r from the axis of rotation? The answer is 100%. My coefficient, or my equation for I of point masses is mr squared. I'll put that over there for us. A point mass has a rotational inertia of mr squared. Okay, so I've gone ahead and said, all right, if I'm going to prove this to be true, then mr squared is a point mass. I've got that. Okay. Let's see here. Now I got to think about the angular speed of the ball. Well, the ball is moving on a straight line. So I'm not sure it has angular speed right now, but I do know a bridge equation I can use. I do know that I can call this, well, let's call this V over R. It's not moving angularly yet. It's moving on a line. It's moving at a radius right before it hits this of R. So I can call this V over R. Let's simplify. I end up with my initial angular momentum for the ball being mRV. This is my initial angular momentum of the ball. Okay. And then I can solve for initial angular momentum. And so I do. And then after the collision, we were stuck watching this thing rotate until it came to a stop. Now, I don't know exactly what the velocity was after the collision. And we can call this like initial angular velocity, immediately following the collision. Like pop, 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 pop. I don't know that. I do know it comes to a stop. So I think I had to, like, in order to prove this, this actually isn't the final angular speed. It's actually this like weird initial angular speed. It's like initial part 2. That's what I was looking for, is immediately following the collision. So I'm going to change this to like initial 2. If this was initial 1, right? Like this is now initial number 2, immediately following the collision. Initial 2. And this is where things got a little weird. We had to use our data. We had to use the change in the change in theta and time to find initial number 2. And we did that using some kinematic equations, all to eventually support the idea that the initial speed after the collision multiplied by I of the windmill plus I of the point mass ball plus I of the point mass magnets were in fact equal. And what this proved to us was exactly what we were looking to prove before. And that is that objects moving linearly have an angular momentum about an axis of rotation, just like our point mass could be modeled with angular momentum around the axis of rotation of the windmill. Folks, like I said, that's all this unit had in it. I mean, it's old stuff. It's similar concepts to what we have covered before. So there's not really anything new except for vocab. New vocab, similar concepts. We can do 10 minutes of questions. So let's go ahead and look at this chat. Something moves translationally, Sasha, if it moves on a line. Thanks, Alex. Why is it different for point B and C, Amina? Let's be different because at point B, at point B and C. I think you mean C when the ramp extended up. The reason why is when the ramp extends up, the object that is rolling actually as it goes up the ramp slows down rotationally. Whereas when the object launches off at point B, it has nothing to slow it down rotationally. It just keeps spinning. Meanwhile, the K translational converts over into UG, and so it goes to a lower height than something that might go all the way back up the ramp that has something that's slowing down the rotation. Is it always UG equals K rot? UG plus K plus K. I mean, if you mean down a ramp, like when an object rolls down a ramp, if it's rolling without slipping and there's only static friction present, yes, right? UG will convert itself into translational motion with K and rotational motion K rot. Now, if it's already moving initially, then maybe UG plus K already. Like it just depends. So I am never, ever, ever going to say always. So you're not going to trick me. I mean, I'm not saying always, but yes, usually if the object starts from rest, UG turns into K translation K rho. If you don't cancel out things in the equation, will you get the same answer? Brianna, I think you're talking about like algebraically, if you're going to solve for something and you don't cancel values out, maybe, right? The problem with that, and the reason we cancel variables out is because often we are not given certain values, or we are given certain values like mass to mislead us. The example of that is if you did ramp races where you rolled objects of the same shape down the ramp. And in my class, we rolled a hollow cylinder, two different hollow discs, hollow cylinders, a large one and a small one. And we rolled two different spheres, solid spheres down the ramp. We noticed that both of the hollow discs made it down the ramp last, and both of the solid spheres, regardless of their weight and size, made it down the ramp first. Now, that's something you might know instinctually, but the reason we cancel variables out is because mathematically, we can kind of make an argument to say, hey, mass and radius, they don't matter in terms of how quickly things accelerate. So, Brianna, that's maybe why we cancel things out. If you're given all the values, if you're given every single value you need to solve a problem, you will absolutely get the same answer compared to someone who cancels it out. Alex says also, yes, it's easier if you cancel it out sometimes. It certainly can be. It can certainly be easier if you're comfortable going all the way down to your base variables. Absolutely. If that freaks you out a little bit and you don't need to cancel things out and you're afraid you'll cancel the wrong things out, maybe avoid that until you absolutely have to. But Alex brings up another good point. Alex, you are absolutely on fire in this chat right now. This is the point I was trying to make earlier, Alex. If you do cancel things out, it's easier to like accidentally cancel something out. Make sure you're always labeling things like too much, right? This is the mass of the disk at the top of the ramp. This is the radius of the sphere at the bottom of the ramp. Like that's probably overkill, but like go ahead. Evan, I think I was making an assumption that the windmill was a disk. It was just an assumption. You can go back and listen to that again, where I say it's just an assumption. When is R radius versus distance from the center of rotation? R is always distance from the axis of rotation. And I say that, period. R is always the distance between the center or the axis of rotation and the edge of something. That's regardless if you're talking about torque, if you're talking about I values, no matter what, R is that distance, okay? When I'm thinking about like, sometimes it is like, if I think about a sphere like this, right, it's rolling down a ramp, I think about here's my axis of rotation, what's my I value? Well, I need this R right here. Okay, well, that R value is also a distance R, right? It's the distance from the axis of rotation to the edge. If I think about a sign that's hanging over here on a wall, and I want to find this tension, like the torque from the force of tension, well, then it's Ft times R sine theta. Well, guess what? That R is still a distance from the axis of rotation to that force. R is always both. It is always the radius of an object and also the distance from the axis of rotation to the edge. Absolutely, it is always both. That's an interesting question to say, when is it each? It's always both. R always stands for radius. I mean, yes. Sometimes you'll see it called even L in some textbooks, like length of lever arm. Also, yes, R is radius around a circularly moving object. Amy Ward about point masses. I think I talked about point masses. Why is the magnitude of the momentum of the total system equal to the magnitude of the initial momentum of the wooden disc? Yeah, Amy, the initial momentum is the momentum of the wooden disc plus the other disc. True, Amy. So Simon and Amy, and then Allison kind of cleans this up, because at first the only thing moving was the wooden disc. Since there's no net torque or net force, it stays the same. Absolutely. So Simon, Amy, Allison, great discussion there. Absolutely the case, right? Because the wooden disc is the only thing containing angular momentum initially, it is equal to the total momentum of the system, because no outside net torque, so total momentum stays the same. Why are there 3 momentums on the right side? Windmill, mass, ball. Thanks, Mira. Whoa, I jumped way down. Windmill, mass, magnet. Windmill, ball, magnet, right, Mira? There you go. Yeah, exactly. What do you mean by mass? Oh, there's masses on the windmill. There were not masses on the windmill, though, Mira, right? So with the eye of the windmill, we had the windmill and the ball that hit the windmill and the magnets. Our class, maybe other classes had masses. If you did, I don't know, right? Like, but wait. So the magnets omega and I is also, well, yeah, Alex, it has to be, right? Because that's part of the mass. That mass is also part of the system, right? It's heavy. It has some mass to it, so it's going to resist changes in acceleration. So yes. Xavier said, my teacher emailed it to my class and I was studying anyway. I don't know what Xavier and Josh were talking about. Can I just say? I don't know what they're talking about. Sorry, boys. Why is the magnet included in L final for the windmill problem we just went over? Alex, I think I explained it. I hope I did. But again, the magnet has a mass. That mass is resisting rotation. Therefore, it has rotational inertia. That's the definition of rotational inertia. Do mass and radius not matter when comparing two solid spheres? Allison, exactly right. Well, hang on. I said exactly right. I made an assumption. I think, Allison, you're asking me, do mass and radius not matter when comparing two solid spheres that roll without slipping down an incline? The answer is absolutely yes. The reason why is that both objects experience, the reason they roll down the ramp, as we kind of talked about, was their offset of the surface touching the ramp and where their axis of rotation or their center of gravity is located. So because of that difference, right, they roll down the ramp. Now, gravity, while it accelerates things at the same rate, also acts on objects differently. What I mean by that is like my gravity is much, much, much larger than Mrs. Gustin's gravity, right? She is much tinier than me. So we experience accelerations the same way, but my mass is larger. Now, when that means things roll down ramps, that means objects that are heavier require a larger force to accelerate. Well, objects that are lighter also require less force to accelerate the same rate. Sizes are made up for in acceleration. So the fact that I'm larger means I've got a larger weight force on me, means I've got a larger normal force on me, means I've got a larger static friction force on me, which produces my torque. Someone that is lighter has a smaller weight force on them, has a smaller normal force on them, which means they've got a smaller force of static friction, producing a smaller torque. Either way, they balance themselves out based on their shape as they roll down the incline. So Allison, I'm not sure if that answers your question or if that confuses you more, but it's the interplay of the fun equation. Force of friction equals mu Fn. Fn comes from Fg. Don't forget the fun equation. It's one of those sneaky things that always pops its head up. When you have things going down a ramp, does the steepness affect anything? Mira, that's a great question. The steepness doesn't affect anything until the object starts to slip. Okay, if you reach a point where your object is the angle is so great that the object starts to slip, well, now the center of mass actually can't move past the point of contact on the surface fast enough. Therefore, we see them moving together. We call that slipping. So our friction goes from being static to being kinetic. So to answer your question, yes, it matters. Does it matter in this class? Like, that's a complicated math problem. Probably not going to matter in an algebra-based class. Allison, I'm calling you Allison, and it appears that you go by Allie. I apologize, Allie. No. Jack, if momentum is conserved, does that mean the moment of inertia would stay the same since momentum wouldn't change? No. In fact, momentum is conserved, especially when our shapes change. This is the whole pulling our arms, and we watched the video of Callista doing it. When she like pulled her arms in and then she put her foot over her head and she was spinning faster, she was changing her moment of inertia or her rotational inertia. But the whole time, because there's no outside net torque that she was producing on herself or putting on herself or pushing off of the ice, like that allowed her allowed her momentum to be the same. So no, the only way we change momentum is if we have an outside torque. Momentum explains changes in I, resulting in changes in omega. If a ball is traveling, Ezra, I'm not going to answer that kind of question. If a ball is traveling at a V and is 5 meters away from a plank of wood, and it's 4 meters from the center of the plank of wood, would the R in Ezra, your R value is going to be the distance between the object moving with a velocity of V and the point right before it collides with the plank of wood. So I'm not clear on what the question is, but wherever that object is about to hit that plank of wood, that distance, that's your R value. Alex, yes, it does depend on where you place the axis of rotation, absolutely. But when objects do in fact rotate, It is much, much, much simpler to place your axis of rotation at the fixed point, at the actual axis of rotation. Even though we can still do the math differently, if it's not there, we want to make sure we're getting that axis of rotation in the right spot. Yeah. Have the same mass. If three objects, solid sphere. Nicole, you're going to have to look at their I values, right? In order to figure out which one is going. So the one that's going to go higher, this is very similar to the seminar problem. The one that will go higher is the one that will store less rotational energy. How do you know which one's going to store rotational energy the most? Look at their I values. Look at their mass distribution. Which one has more mass at the outsides? Which one has more mass at the insides? Based on that, we'll be able to see which one has the fastest translational speed at the bottom of the ramp. And therefore, you can figure out if it has the most translational speed, it will get to the highest point. We already covered that a little bit ago. Whew. If there is a collision, okay, Sasha. If there is a collision, does the object stick or bounce? Yes, Sasha, it does. I'm not sure we've come across an inelastic, an elastic angular collision. But if an object is moving on a line, boom, and bounces off back this way, like boosh, boosh, and this thing starts to move rotationally, we'll need to use MRV for this object before, and then MRV as it bounces off back this way. Don't forget to make sure you understand that momentum is a vector. So positive velocity, negative velocity, and also include angular momentum for this. So I omega for this. So is it possible? Yes. That sounds like a super like AP conceptually question, like from College Board, but I would say like MRV, and I omega. That's how I would probably model that mathematically. And then you just plug your numbers in and solve. Look at I. Solid sphere has more velocity, since it is smaller. Right. The smaller the I value, the more acceleration it will see down the ramp. Ratika, what's happening? How does the rotational inertia of certain objects impact? Ratika, go back earlier. I think Alex just explained it there because I think someone else asked it earlier. Nicole asked it earlier. If you go back this way, we're talking about looking at your conservation of energy expressions. Look at which one can accelerate down the ramp the fastest, and typically does that if its mass is less distributed around the axis of rotation based on shape. That will tell you which one accelerates down the ramp the fastest. Are you answering review packet questions? Why did this get jumped like that? Not really. No, I'm not going to do it tonight because we're almost at an hour already, so I'm probably not going to do review packet questions. The packet key should be posted on Canvas and Google Classroom pages. I know my students are going to be like, Mr. Gus, it's not posted yet. I know. I got home from basketball, jumped on here. I promise I'll post it as soon as I leave this thing. So I'm not going to answer review packet questions. They're on there. My advice, there's one question where there's like a lever arm and a ball moving at it, and it's like a kind of point P and a ball. Like, my opinion, skip that question. Don't do that question. It's my secret opinion that I just put on a public YouTube page. Simon, I'm not gonna do review packet questions. Sorry, man. The work should be there. The work should be there. Try to follow the work. I'm not doing review packet questions. I think number 17 is what I was talking about. Number 17 is the one where there's like the point P. Knock it off. Don't do that one. Yeah, like I said, there's R perpendicular. There's all this weird stuff. It's an old school. That's a physics question from when I was back in this class. It's an old school question that just doesn't really pop up anymore. Sasha, you're so smart, Alex. I kind of agree, Sasha. I think Alex is absolutely rocking this comment section. If something is rotating, does every point. It keeps jumping around on me. If something rotates every point. Angular. Ezra, if something is rotating, does every point on that rotating object have the same angular velocity? Yes, absolutely. Right? Absolutely. If something is rotating, Angular velocity is your angle swept over time. There is no way an object can rotate around its center and every part of that not rotate at the same rate. If it did, we'd see something like a tornado where the inside is spinning faster than the outside, right? It would be like this weird, like shaped thing. So yes, everything on a solid object has the same angular speed because of angle over time. I think there's a disagreement about one of the review problems. If it's that number 17, just cross it out. One, two, three, skater, no problem. I don't know who you are, 1, 2, 3, skater, but you're always here, so no problem, kiddo. Marcos, will you have all lab formatives graded by today? Well, Marcos, I had them all graded earlier today. If you had turned them all in, you'd have them graded. I don't actually know. Marcos, you probably turned them all in. I will try and regrade them again. Can someone drop the Iowa score in the chat? I'm over here doing physics, and I got to know if Iowa's going to win, or if they're winning, or if they won. Alex, can you be my tutor? Oh, now Alex and Sausage are just having fun in the chat. Thank you, Mr. Gustin. See you, Amina. Ezra, no problem. That sound effect was nice. Xavier, I feel like I always see your comments too late. Yes. Thank you, Mr. Gustin. And Alex, this was helpful. Yeah, Alex, great job. See you, Amira, Hiva, Marcos. Kaush, does that mean Iowa won? 77-62. Is that an Iowa win, Kaush? See you, Mira. See you, Simon. Iowa game. All right. Thanks, Kaush. All right, everybody. All right. I'm out of here. Have a good night. Check your review guides. Good luck tomorrow. I'll see some of you in seminar. Otherwise, have a great night. All right? Go Iowa.